All right, welcome to the first class for the EGR/PHY 321 Engineering Dynamics. We're covering Chapter 17 today, Stephen F. Austin State University. We're going to begin working on problems in plane motion for rigid bodies, and now we're going to be looking at energy and momentum methods. Okay, so typically with these kind of analysis, the way we're going to kind of revisit what we had looked at in chapter 14, where we started looking at the effect of going from work and energy, right, and conservation of energy, using those methods to solve for problems. We can apply that to rigid bodies. And so the first application for this is going to be through chapter 17. We're going to be looking at plane motion specifically. So these problems will be in two-dimensional. Okay, and we're going to expand this. We're actually going to go into chapter 18. So there's going to be some updates to the class. I'm making some significant changes to the class. So please pay attention to that in this video. The first few minutes are going to kind of overview how we're going to kind of work out the rest of the class and make some pretty significant changes to the course. But for chapter 17 specifically, we're going to first look at section 17.1, which describes energy methods for a rigid body. So we're going to look at energy methods. I don't mean to cross that out. I meant to highlight it. We're looking at energy methods. And then in section 17.2, we're going to go through momentum methods for a rigid body. Once again, still in 2D, right? And then in the last section, we'll cover eccentric impact. Now, the book shows this picture of this gymnast, and he can be described as, or can be kind of modeled as a rigid body, in which we can describe the motion using these methods of energy and momentum, kind of similar to a lot of the problems you're going to be working with at the end of the chapter. So let's take a look at a little bit about what's going on in the next few weeks. Specifically, we're on schedule with CLO 11 and 12, right? We are going to assess these two. These have not changed. We're going to assess these two, 11 and 12, on the days of the 20th, which is down here, and the 27th, right? So that only leaves really one extra CLO, right? So CLO 13. So we're making some changes in terms of what we're going to cover in the class. So considering the fact that the class has gone completely to Connect, what I'm going to elect to do is we're going to cover chapter 18, and we're going to forego Hamiltonian and Lagrangian because I don't have a good way of continuing assessment with that material here. So some big changes happened to the schedule here, and I've uploaded a new version of the syllabus that kind of goes over this. But ultimately, what's happening here is we're moving some of the CLOs, right? So the final exam is going to be a Connect assessment. And typically what I'll do, or what I will do, is I will set up Connect assessments for all CLOs, right? And you can choose to work any of those to update one of your CLOs that you might not be happy with. So you'll have the opportunity to work any of the CLOs that are available. I don't intend for you to work all of them, right? So this is kind of what we were doing before. That's how I'm going to mimic the final exam in this class. So that being said, how we're going to carry the class out from going forward. So today is going to be the 6th, right? So we're on the 6th here. And the way that I'm planning on doing this is I'm going to work through the material from the textbook. You're going to kind of read through, which, by the way, the reading assessment is going to be due on Wednesday. And then we'll work some example problems out on the following day. And that's how each of these sections are going to go through. We're going to kind of cover the main material, however long it takes, and then we're going to do some example problems. So I'm going to work through some of the problems. Maybe they're homework problems, maybe they're sample problems, or a combination of two, so I can kind of help drive home these principles. Considering that it's not quite clear as to the work that's required for this Friday, because it is the Easter break, right? We have been told that we're going to still work through that. So what I've done is I'm basically saying that you don't have to attend this class on Friday, right? I'm not going to take an attendance quiz, but what I'll do is I'll post a review for chapter 16. So that's going to help prepare you for CLO 10, and you can watch that at your leisure and kind of work with those problems as you kind of see fit. Going forward, you can see that the way that I've broken down each of the classes, we're going to kind of cover the main material on the first day, and then work examples on the second. So each section from here on out is going to take 2 days of class time. And then lastly, we'll have a review, which goes over everything that we need specifically for Chapter 18. All right? So how does that change the CLOs in the syllabus? So this is once again in the syllabus, so you can refer to that. I have changed the final few CLOs. You can see now there's only 15 total. And the one that I've changed mostly is CLO 13, and I've removed the CLO 14 that was from before. So CLO 14 is now for homework, CLO 15 is for the chapter reading, and then CLO 13 is going to be covering section or Chapter 18, or our material for Chapter 18. I've had a few questions about CLO 6, which is the midterm. There were some issues with the grading there in terms of how we're setting up. So I'm just saying out here, right here, CLO 6 will not be assessed. It won't be removed. It will be removed from grading. We're not gonna. It's not going to come into your final grade. The new grade point distribution is posted on the syllabus. That's not going to be assessed. And to forego, since there are some issues with that midterm, I'm going to remove the lowest CLO from 1 to 5 to kind of act like you have replaced that with a good grade, so to speak. So I'm just going to forgive that grade, so it's almost like your lowest grade will be removed, and this will go into your final grading for the class. CLOs 7 through 13 are going to be basically only assessed on D2L. On Connect, right? So the Connect grade that you receive. Now, right now, the way the D2L is set up, it's still averaging all these grades. I apologize for that. Just take the highest grade of either of the CLOs. That's what I'm going to do with my final grade book, and that's how I'm going to post your final points, point structures as we go through the class. Okay, so those are the big announcements for this portion of the class. I understand that there might be some questions or some issues with this change. I'm more than happy to answer those questions. You send me an email. We can set up a Zoom session where I kind of work out or work with you. If you have any questions about the problems, or if it's unclear, the material you're responsible for, please let me know as soon as possible so we can help that out, right? So some pretty big changes here. I think the biggest change is that now the points are going to be from 150 points or total, right? So 150 points total, because we're moving CLO 6 and we're moving the CLO 14, which was the material on the Hamiltonian Lagrangian. And so now it's brought it down from 170 to 150. So that's changed the grade distribution, right? And so the way that I kind of calculate the grade distribution is basically if you get a 0.9 multiplied by 150, right? Anything above 0.9 multiplied by 150, you get an A, and the same thing, 0.8 times 150, basically between these two, you'll get a B, and so on and so forth. And that's how I get those point breakdowns. So if you have any questions about that, please let me know, and I can work with you, and we can kind of cover that material. All right? So with that being said, today what I'm planning on focusing on is just the material for section 17.1. Okay, so we're covering really the only material that's going to be covered in CLO 11. So it's kind of an important aspect. The homework for Chapter 17. So the reading assignment for Chapter 17 is posted, so it should be available to you. It's going to be due on Wednesday at 5 p.m. It shouldn't take too long to go through. It's not that big of a chapter, so make sure to cover that or review that material, and so we can kind of drive home some of the concepts that you see there. Chapter 17 is split up into two homework sets. The 17 part 1 is going to be due on Friday the 17th. That's before the CLO assessment for that part of the chapter. And then Chapter 17 part 2, that's going to be collecting 17 part 2 is going to include problems from section 17.2 and 17.3, and that'll be due on the Friday the 24th, which again is before the CLO assessment for that particular section. So that's kind of how we're kind of going the same pace in terms of CLOs and the homeworks and what everything's due. So just kind of keep along with that, and you should be fine. All right. Once again, I'm just going to remind you, if you have any questions whatsoever in terms of where the grades are assessed, please send me an email. I could try to answer it that way, or you can set up a Zoom appointment. So let's talk a little bit about principle of work and energy, right? So before in chapter 14, we had used this relationship. We kind of had said that, whenever we have our initial kinetic energy, T1, plus whatever might change in this internal, or change in the all the forces that are acting on those particles, so the various work of all the forces that are acting on the particles would result in the second kinetic energy, right? It's involving problems with velocities and displacements, and really work and kinetic energy are scalar quantities. Okay, so these are not vector quantities. We treat this as scalar operations. So how do we kind of break that down? We had kind of re-expressed this in terms of, well, almost like a conservation of energy term, right? We'd say T1, whatever my kinetic energy, plus whatever my gravitational potential energy, VG1, plus whatever my elastic potential energy, VE1, plus whatever my non-conservative forces like friction and such, going from 1 to 2. So this would be my initial energy accounting. That's going to equal whatever my second kinetic energy plus whatever my ending potential and gravitational potential energy plus whatever my second or the second state elastic potential energy. Okay. So these non-conservative forces are almost always assumed to be taking away energy from your system. That's why I put it in the left-hand side of the equation there. So this is kind of the main relationship that we have worked with, and we can apply this to rigid bodies, right? The kinetic energy of a body really would come back from the systems that we work with, right? Where you'd say the total kinetic energy is just going to be equal to 1/2 the summation of all the particles in your system. So in this case, this is the particles that are making up your rigid body. We said that's equal to the summation of each little tiny piece of mass multiplied by its velocity squared. Okay, so we're summing up all these, the kinetic energies of all these particles, but what we have to say, or what we suggest with a rigid body, is that a rigid body can be assumed to be multiple particles that are kind of working between each other, right? And that's ultimately what we're kind of getting at here, is that we can associate each of the specific particles, but then we can look at what are the forces internal and then what are the forces external to this type of analysis. So that's the kind of big thing here, is, or at least the initial part of analysis, is that we're first going to assume any kind of internal forces. So let's look at it, think about what's going to happen if we have two particles in a rigid body and they have some forces that are internal forces that are acting with each other. Since they're internal forces, the forces are going to be equal in magnitude and opposite in sense. If I was to take a look at each of these particles and their motion, right? Let's think about location B. B might move a certain distance, and we're going to call that distance dr prime. A might move a certain distance, and we call that dr. Now, dr is not equal to dr prime generally, right? Now, we could have just translation where that might be the case. But if we're assuming that they're not the same, that's fine. But let's take a look at the forces in the directions in which they're going. Okay? What we know is that the relationship is that AB is equal to A prime B prime. So the distance between these two forces, right, are still equal to each other. The small displacements are not equal, but the total displacement, right? So AB, the displacements along the line AB are going to be equal. So if we can understand this, that means there's really no change in distance between these two internal forces, right? Therefore, we can state that the network of all internal forces is 0. And that's a pretty big statement, right? So now when we're applying our work and energy methods, we can assume that any internal forces to our system is going to result in 0 work, because those particles are not moving with respect to each other. And that kind of going forward says that now all work and energy, or any work that's done, has to be done by forces that are acting outside or external to the body itself. So that's a pretty big important statement here. Let me see, can I do this? Hello? My iPad's not working very well. There we go. All right. So now let's think a little bit about work of forces that are acting on a rigid body. Now, generally what we had said before, this is kind of a restatement from section 13.1, right? We'd say that the work between any two states, right, would be equal to the integral of the force dotted with the dr, right? So the change in position. And so here we're looking at any kind of particle or any kind of body that's moving, right, in which we might have a force in a certain direction, okay, and then a dr in another direction. And we're saying that along that path and the angle between them, right, so the angle between them would be this alpha, and we can restate it that along a kind of a path that's going from whatever this motion might kind of describe itself as being, we can assume that the total work that's being done is going to be that force. Now, remember that this is kind of said that if we have, say, for instance, the particle is moving in such a way, right? So say, for instance, the particle here, if we were treating it as a particle, right, we'd say maybe our force is this way, and then in this case, we have, this would be like my dr, right? If there's a 90-degree relationship here, we understand that no work is going to be done by that force, right, because of that cosine of the angle between them. So this is just a general representation. So we say, all right, now we can treat motion of a rigid body as being like, all right, well, we can translate the body, but then what are the work that's done by any of the rotations that we might see of a specific body, okay? So in order to analyze the work of forces that are acting external rigid body that come from any kind of rotation, we can consider the network of two forces, right? An F and negative F. And these form a couple, right? So if you remember a couple from previous analysis, right? The couple kind of is defined by, it's got the same magnitude of force, and it's just separated by a distance r. And remember, we can almost say that it's analogous to saying that my RF magnitude, right, would just be equal to the magnitude of a moment. And we can replace these two. So the couple and the moment can be replaced or transposed. And really what changes here is that these ratios have to stay the same. So the distance and the magnitude of these forces have to stay the same. But this is ultimately the kind of governing relationship of that couple moment. But if we're just looking at the individual forces themselves and the type of motion that we're expecting to see, we can kind of break it down and say, all right, well, obviously these forces are going to create motion. And we're assuming, in this case, that here we have some dr1. And in here there's going to be some dr, and I'm going to just call this dr maybe 2 prime or something like that, right? In which there's going to be a total motion that's different, but we don't quite know. And we can break that down into the two components that are seen here, right? So we'd say we superposed dr1 on top of that, and then we add a little bit change that comes from the rotation. So there's going to be some movement or direct translation, and then there's going to be some rotation of this body. So if we were to act or look at the total work, the change work, right? So it's really the F dot dr for each of these relationships, right? So if I'm saying, all right, then the total change in work is going to be equal to the summation of all the little tiny forces and their tiny changes in distance. So we'd say, okay, we have to apply one from this, and then one from this. So there's 3 terms here that we have to consider. The first being we're going to have an F dot dr and a negative F dot dr, right? Because we have the forces the same magnitude, they're just in different directions. And since dr is the same on both sides here, that means these two are going to cancel out. And then we're left with this tiny change, so this force F dot dr2, which is left from whatever we have during rotation. So whatever we have during rotation can be defined from whatever the change in angle for the rigid body would be. And we can replace the dr2 is really just equal to ds2 for a small angle approximation, right? So considering d theta is very small, that means it's the same linear distance. If we do that, then we can realize that ds2 is really just going to be equal to whatever my r is, remember, because r is the same right here, multiplied by d theta. So I replace this into my equation here, and then I get an FR term that shows up out front, and then we can replace FR with the moment, M, we see there. And now, if we want to get the total work from 1 to 2, that just comes from this couple, I can integrate both sides. And when I do that, I get the integral from whatever my theta 1 to theta 2 is, okay? And I have moment inside of the integral there. One step further is that if we're assuming through this point that m is constant, I can just pull this out of my integral, and then I'm left with the integral of d theta, and so that gives me theta 2 minus theta 1. This is only the case if m is constant. So this would be my u from 1 to 2. So that's the case where we're looking at a couple. So if there's a moment that's acting on your body, then this would kind of tell you, or at least show you, what the total work would be from just the rotation of the body itself. So let's go through some kind of specific statements that I think are really important towards the end of this section, in terms of what forces that are acting on rigid bodies that do not do work. Okay, so it's something that you have to consider when you're analyzing these problems, right? Because not all the forces are going to do work. Some of the ones that we kind of point out here is that, say for instance, I have a bar, right? And there's a pin, and this is a fixed connection. Okay. If I have any forces that are acting on that point, right? That's a fixed point or a fixed connection. That's obviously not going to do any work, right? So this is especially if I have some sort of reactions of a frictionless pin. So if I were to kind of take this out and do a free body diagram, those forces are not going to do any work because the point is not moving, right? So the ds or dr term is 0, so I have no external work. That's pretty easy to see. Another one is that if we have forces acting in a direction perpendicular to the displacement of their point of application. An important aspect or pertinent thing to think about, so say for instance I have a body and it's moving along a frictionless surface, right? So it's moving in this direction. The normal force, right? So if I were to replace the ground with a normal force, right? The normal force here is going to do no work. Okay. Same thing goes if I have motion of a body and weight, right? So for instance, if I have a baseball, a baseball is traveling. And it's going in a specific direction, right? So let's say it's acting horizontally. The weight here is going to do no work. So those are the two primary cases there. And then the last one is can be a little bit challenging to see, but it's something that's very important, is that if we have friction force at the point of contact of a body rolling without sliding. Remember we had spoken last section about this idea of a rolling wheel, right? So if I have a rolling wheel along a surface, right? I know there's going to be a friction term that's going to work against us. Okay, that friction force, if there is no sliding, okay, so it's no sliding, this force is not going to do any work. And why is that? Because if we're looking at the change in this point, so we're saying here the point of contact, this location is C. So that change is relative to that point, right? It's not doing any specific work because the VC term is 0. Okay, so there's no VC relative to the point on the surface there, so it's doing no work. Okay, so it's a little bit less clear, but it's important to recognize because you might have some problems in which you might have to consider that. So those terms do no work. All right, so moving on, let's look at this definition. So we kind of defined or set up this, well, how do we define the total kinetic energy of a body in plane motion? And we kind of separate, we said, we know the work terms, we can separate the work terms by the displacements and whatnot, and we looked at the rotation, but how do we derive, or how do we look at kinetic energy of a body in plane motion? So what we can do here is we can split up the motion of any particle within a system as being, let's look at particle, or the G as the mass center, right? Mass center is moving with some velocity v bar. So obviously this whole rigid body is going to have kinetic energy that comes from that motion. So we add that first term in here, the 1/2 mv squared, and this card is v bar squared. we also have to consider the motion of each of the particles that are surrounding it. So if I were to pick out one particle, in this case pi, and I were to look at the motion that's associated with that, it's going to have a motion associated with the motion of the whole body, in this case v bar, and it's also going to have motion that's associated with the rotation of the body. So now that we're developing rigid bodies, we understand that it's not just translation, but it's also rotation we have to worry about. So the particle is going to have some velocity component, right? Vi prime, and remember the prime is relative to the center, the mass center of the body, and it's defined by this Ri prime. And see, these two form a 90-degree angle. So if we're looking at this velocity, right? So now we can break down, or what our velocity would be, okay, is going to be broken down by the v bar, right, and then the vi prime. So now we're looking at the motion of vi prime. Motion of vi prime. If we were looking at this system, we can relate and say that really the vi prime in this case is just going to be equal to whatever my ri prime multiplied by omega for the body. So if I put that into my relationship here, what I'm left with is a summation now, and we put the parentheses here to represent this r squared mi, because that represents the mass moment of inertia, right? So now I can replace this with I bar and say that my total kinetic energy of a rigid body can now be simply stated as being 1/2 mv bar squared plus the I bar of the body multiplied by omega squared. So here the kinetic energy is associated with the motion of the mass center g, and the kinetic energy associated with the rotation of the body around g. And that's kind of that. From here on forward, this is how you're going to apply or look at these types of problems. We can also look at the case where we have non-centroidal rotation. This is in the sense if, for instance, if I have a fixed axis at location O, and I was to describe the kinetic energy of this body alone. The body alone now is going to be represented by just the kinetic energy of each of the particles, and I sum those up, remembering that Vi here is then going to be equal to Ri omega, right, given right here, and then I replace that into my relationship, and then I'm left with this thing, which is the mass moment of inertia, but this is not centered about the geometric center, it's about some point. Okay, so we can also define, if we have fixed axis rotation through O, that my kinetic energy would be 1/2 I-O omega squared. Now remember here, I-O has to be developed if you only have I bar, which is typically what we give you. Remember we had said that I-O is equal to I bar plus whatever my M, and this would be R bar squared. Okay, so we have to, if you only have the centroidal mass moment of inertia, you can relate that back to I-O or any position with that mr squared, as long as you know the distance between those 2 points. So now, how do we apply this to systems of rigid bodies? Well, it's pretty simple. It's just restating and say, all right, we're going to take this relationship, the same relationship we're using as well. We can apply the same principle to systems of bodies, right? Where here, the arithmetic sum of the kinetic energies of all bodies forming in the system, then take into account their kinetic energies at state 1 and state 2, and then we look at the work of all forces acting on various bodies, whether these forces are internal or external to the system as a whole, right? So what this means is now you're looking at multiple bodies and we connect them to each other. So the total system still has internal forces, and right, we said before for rigid bodies that those will cancel out. But if we're looking at separating each of these bodies out, right, we can say that the internal forces that occur in pairs that are equal and opposite forces. So this is the case for looking at maybe pin connection, right, blocks and pulleys connected by cords, mesh gears, so on and so forth. We can make relationships between these forces, these internal forces that are acting between the points, where if we were to group everything together, the internal forces would have zero work. But if we're analyzing each body in its own right, those works internally will have representations which will cancel each other out. Okay, so the work on the total system reduces to the work of the external forces, and we know the net work of the internal forces is equal to 0. This can help us kind of analyze problems in which those forces are kind of acting against each other. So this can be applied to systems of rigid bodies. Okay, so this is an important statement from the aspect of what we're working with here. Okay, so let's take a look at an example here. So here we have a slender rod, right? In which we know, right? We know the mass of the rod, right? We know the length of the rod itself. And we know that the center of gravity is acting at point G, which is just half the distance, right, of the mass of the rod itself. Okay. The unknowns here, if we're going to be asking this particular problem, we want to find what are my angular velocity of the rod itself. Okay, and the way that the motion is prescribed is we're going to say that the motion of B, right, is only going to go down, and motion A is only going to go to the left or right. Okay, motion A cannot go down. The theory here, remember we had said now we're going to apply the total kinetic energy. We're going to look at the total kinetic energy and potential energy. We're going to use conservation of energy. Say kinetic energy of state 1 plus the potential energy of state 1 should equal the kinetic energy of state 2 plus kinetic energy of state 2 plus the potential energy of state 2. Okay, so there's no springs here, so we're only left with gravitational potential energy. And so when analyzing this, we first say, okay, well, at the initial position or initial case, we have T1 is equal to 0 and V1 is equal to 0. So we're going to set the datum in such a way that its potential energy at the beginning case is equal to 0. The next thing we have to consider is that, yes, the body is going to fall in some way, right? So we have the forces pulling this slender rod down, and we know that there's going to be some change in the potential energy. So the kinetic energy, state 2, we can start with our general theory for kinetic energy, right? Which we said is 1/2 mv bar squared plus 1/2 the I bar omega squared, right? And so that's my relationship. We're looking at state 2, right? So we're going to replace the V and omega with 2. And so to get a better relationship here, we can recognize that the velocity v bar 2, since it's acting right in the middle of the bar, and really it's only coming, the motion, since A is not allowed to go down, the motion is really coming from the rotation here. So our V2 is really equal to 1/2 the distance L, right? Because that's the center of the body, multiplied by its omega. So if we put this into my relationship for T2, we get this is equal to 1/2 m, and this is going to be 1/2 L omega squared plus the 1/2. And now we think about the slender rod. So looking at my last page in the textbook here, the slender rod is going to have a mass moment that's going to be 1/12, and that's going to be m L squared. So that's my I bar, and then I have my omega squared. Okay. I guess one other thing I neglected to describe here is that we also know the theta at the time at which we are trying to analyze this motion. That's going to become important in a second here, because my T2 now is going to be equal to 1/2 m, and this is going to be 1/4 L squared omega squared plus 1/2, and we could pull the m out here, and that's 1/12 L squared omega squared. So we can combine these two to say that my kinetic energy in the second case is going to be 1/2, and then we can say it's really just 1/3. So 1/4 plus 1/12 is 1/3. That's equal to this m L squared over 3 multiplied by omega squared. So that's kinetic energy at my second state here. And then lastly, if I'm continuing on the analysis, I have to consider what my potential energy at state 2 is. So potential energy at state 2 can be found by looking at the drop, the distance in which it changed. Okay, and so since we have that's equal to the 1/2, or really negative 1/2 of the weight multiplied by the distance that it went, right, the L sine theta, I can replace this and say it's equal to negative 1/2 mg L sine theta. So now putting these back into my equation, right, my overall equation T1 plus V1 is equal to T2 plus V2. I get this first term is equal to 0. That's equal to my 1/2 ml squared over 3 omega squared minus 1/2 mg L sine theta. My masses will cancel out here. This L is going to cancel out with this squared term here. I can move this term to the other side, and so that I'm left with omega is just equal to 3g over L, and this will be sine theta to the 1/2 power. Okay, and so that would be my answer for this particular problem. But once again, it's just looking at what we can do with, or what we start off with, our definition of kinetic energy, right, which is really what we had gotten in the previous section here, or in this throughout the section here, and then we apply these to conservation of energy. And that's how we use conservation of energy here. All right, so one last thing one last mention that I should make is this idea of power, right? And so if you remember, power is equal to the time rate change at which work is done. So if I take power, it's equal to this du dt. Remember that the work that's being done is really F dot dr, and if I take the derivative of that, dr dt, I get my velocity. Okay. So remember that this is a dot product, so I'm looking at the forces that are directed along my velocity vector. And then if I consider a rigid body that's rotating with an angular velocity omega, right? Remember that's the m d theta that we had gotten. Then we get the d theta dt. I get that my power is equal to the moment multiplied by the angular velocity. Okay, so these two terms for power are kind of how we get if a problem asks for things like horsepower or whatnot. This is kind of a callback to section 13.1. So if you want to kind of review this, go back to section 13.1. You can kind of get extra material there. All right, so considering the time we have spent on this, this is a good place to stop. So I'm gonna hold the video here. I'm gonna have an attendance quiz for the material from this section to kind of drive home some of these principles.